Hello. We're going to be talking about a rational inequality. So a rational inequality is one that can be written with a rational function on one side and 0 on the other. It doesn't have an equal sign, but it has a greater than, less than, or greater than and equal to, greater than and less than sign in between the function and the 0. One way we can solve these is by knowing their graph. We just talked about extensively how to find the zeros, vertical asymptotes, and holes of these graphs. And those vertical asymptotes, zeros, and holes are the only places where the function can really change from positive to negative or vice versa. So I'm going to look at two examples here. One, we're going to be looking strictly at the graph, and the other one we'll be doing algebraically. We can verify with the graph if we like. The first one, we want to use this graph of the function 2x squared minus 4x minus 6 over x squared minus 4 to find the solution of the rational inequality where that function is less than or equal to 0. We're going to be looking at the graph here, and let me get my pen out. Really what we want to do is we want to know where those function values f of x are less than or equal to 0. If we call this over here our f of x, we want to know when that is less than or equal to 0. That's what we're going to try to do here. There's our equal to. So we use this function here, and we have the graph of that down here. Notice that when we're above the x-axis, this function is positive. When we're below, it's negative. The only places where this changes would be at the asymptotes or zeros. I did factor this numerator out, and you can verify that the zeros are at 3, 0, negative 1, 0. That would be this top part factored out. And you can see that by factoring the denominator, nothing cancels out here from the denominator and numerator, that you're going to have vertical asymptotes at x is equal to negative 2, and x is equal to positive 2. Those, of course, you know what happen when the denominator is equal to 0. So setting the denominator equal to 0, we have x equals 2 and x equals negative 2 are the vertical asymptotes. And if you notice, those are really the only places that this graph would change from positive to negative. So I want to know all the places where this graph is less than or equal to 0. I'm going to get out a different color here and maybe change it to a thicker. So I look at these points. Really, the only places it can change are here, 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 and here. Those are the only changes. Where it's less than or equal to 0, well, it's going to be equal to 0 at these points that are 0. So where the numerator was equal to 0, we have to include those points. Other places where it's less than 0, we can see between negative 2 and negative 1, yeah, it's less than 0. The graph is below the x-axis. We can also see between 2 and 3, that's the same bit. But we know that we can include these asymptotes because the function's undefined here. These are our two intervals, the only two intervals where this function is less than or equal to 0. If we try to write that in interval notation, we would say that the function's less than or equal to 0 at negative 2. We don't include that negative 2 to negative 1, but we do include that, so we put a square bracket there. Union, I'm going to use a U for union. And then I don't include 2, but I do include 3. That would be my interval in which that graph is less than or equal to 0. We did this totally graphically. So now let's see how we do one where we don't use the graph. So I'm going to clear this out, go down. And note on this one, it says caution. Since we're solving for a variable, we don't know beforehand if the solution will be positive or negative. So in order to solve inequalities correctly, 0 must be isolated on one side of the equation and fractions cannot be cleared. So really what that means, and this is an important step, is that we have to get one side equal to 0. What we have to do is subtract 3 from both sides. So that's what we're going to do. Subtract 3 from this side and subtract 3 from this side. When we do that, we will get everything on the left-hand side. So we're left with x over x minus 2 minus 3. I should say x plus 2. Minus 3. And that is going to be greater than 0. I have to get this over the same fraction, x plus 2. What I can do is I can go ahead and multiply and divide by x plus 2 to build this fraction up. So notice the first thing we do is we get everything on one side, 0 on the other, then we build that fraction up. Now that I've built that fraction up, I can put both denominators over x plus 2. So let's do that. X minus 3 parentheses x plus 2 all over x plus 2 is greater than 0. Also, the numerator can be simplified a bit. I can distribute that negative 3 through x minus 3x minus 6 all over x plus 2 is greater than 0. And I can finally combine the terms on top. X minus 3x is negative 2x minus 6 all over x plus 2 is greater than 0. And finally, remember, I want to find the asymptotes and I want to find the x-intercepts, so I need to factor out that numerator, and I can do that by taking out a negative 2. Negative 2 times the quantity x plus 3 divided by x plus 2 is greater than 0. At this point, I need to find those asymptotes and intercepts. If I set the numerator equal to 0, of course, negative 2 never equals 0, but when I set x plus 3 equal to 0, I know that x equals negative 3 is an intercept. So this is an x-intercept. It will be at negative 3, 0. And that's the only one. All right. And looking at the denominator, I note that if x plus 2 is equal to 0, that's going to be an asymptote, a vertical asymptote. So I note that x equals negative 2 is a vertical asymptote. So what do I do? At this point, what I want to find is when that function over there is greater than 0. I need to figure out when this is greater than or equal to 0. So I can make a sign chart over here. That's what I'm going to do. So I go over to some empty space, make a number line. I'm going to plot those points. So I'm going to plot those points in order. Here is -3. Here is x is equal to -2. And those are the only two points that I have to consider, because that's the only place where the function can change signs. My intervals that these include would be, okay, let me change the color here. These are going to be -infinity to -3, -3 to -2, and -2 to infinity. Those are my three intervals that I'm going to check. Where am I going to check them? I'm going to check them back into f of x. I want to see if these are positive or negative. I'm going to check them in f of x, and maybe some numbers that I could choose would be x is equal to something like really obscenely small, like how about, or negatively large, I should say, how about -100? And then something in between here, like how about -2.5? And then over here, how about something like 0? 0 is always a good choice if it's available. So what is my function going to be? Is it going to be plus or minus? If I plug in -100 to this red circled part, notice what I get. I get a negative times a negative over a negative. So that's going to be negative times negative over negative. I'm going to get a negative answer here. That's negative. If I plug in -2.5, well, 3 minus 2.5 is positive. Positive times negative is negative. But when I plug in a negative on the bottom, -2.5 minus 2 is negative. So negative over negative is actually positive. So it's going to be positive in between there. Finally, if I plug in 0, I get -2 times 3, that's negative, over 2, which is positive, so that's going to be negative. So it's going to change to negative over here. What I found out is that the interval I'm going to check and going to have when f of x is greater than 0 is going to be this interval right here between -3 and -2. I don't include those 2 points because I don't have an equal sign here. It's no equal sign here. So I don't include those points because I don't have that equal sign there. So my answer is simply going to be -3, -2. That is going to be where that graph is greater than 0. Now we can verify by the graph. So I'm going to pull that up. On the calculator, I have actually put this factored function in. If I just push graph, you can see there at -3, the graph is going to be positive. So from here to here, it's going to be positive. And then this asymptote, the graph will dip below again. So my interval that I get would be from -3 to -2 and everything in between. All right, well, I hope this has helped. Thank you.